In the last lecture, we were discussing unidirectional transport. That is transport in only one direction, and in this particular case we were discussing decay of a pulse. In an infinite medium. Okay. So, the configuration consisted of a plane, okay, at z is equal to 0, okay. The plane is at z is equal to 0, and you have medium extending to infinity on both sides, and at time t is equal to 0, you put a certain amount of mass per unit area into this plane within a spatial interval of infinitesimal thickness, okay, within a spatial interval of infinitesimal thickness. Okay. Mass per unit area, okay, is equal to m. Okay. Mass per unit area is equal to m. So, you put in this mass into a plane of infinitesimal thickness, and then the material that you have put in will slowly diffuse out. Okay. So, initially the concentration field will be a delta function. Okay. So, I will explain what that is later. Okay. Will be only at this particular location, okay. And then as time progresses it will spread. Okay. So, initially it will spread to a small distance, and then as time progresses it will spread to a larger distance, and so on. Okay. So, there will be a spreading of the concentration of this material in both the plus z and minus z directions, and we would like to know what is the concentration as a function of time, okay, for this one dimensional transport. The mass diffusion equation, unsteady, okay, in the absence of any convection, is d partial c by partial t is equal to the diffusion coefficient times d square c by dz square. Okay. So, the second derivative with respect to z. So, first derivative of the concentration with respect to c is equal to the second derivative with respect to z times the diffusion coefficient. Okay. Note that this is a simplification of partial c by partial t plus divergence of V c is equal to d del square c, where we neglect the convective part because there is no velocity, and in the diffusion part there is diffusion only in the z direction. The concentration is uniform in the xy plane. Okay. So, that is the configuration. And since the medium extends to plus or minus infinity, the boundary conditions are c is equal to 0 for z going to plus or minus infinity. Okay. So, as you go far away from this plane, there is fluid without which has to which this concentration has not yet diffused of this particular species. And you also have an integral condition, because whatever you mass that was put in at initial time has to continue to be there throughout the domain for all time. Okay. Whatever mass was put in at initial time has to continue to be there for all time. Okay. So, this integral condition is that the initial mass per unit area that I had put in, okay, has to be equal to integral over the z coordinate of the concentration. So, concentration is mass per unit volume, integrated over z will give you a mass per unit area. So, that mass per unit area that was put in initially has to continue to be there for all time. Okay. So, this is a condition on the total mass. Of course, by symmetry the slope of the concentration field has to be 0 at z is equal to 0, because it is spreading equally on both sides. Okay. And you also have an initial condition, okay, at t is equal to 0, when you have just injected the mass into this domain, okay, at t is equal to 0, when you have just injected the mass into this domain, okay, the concentration is equal to 0 for z not equal to 0. That is, any location where you have not injected the mass, the concentration there has to be 0. Mass is injected, a certain mass per unit area is injected at z is equal to 0. Therefore, the mass has to be 0 wherever z is not equal to 0. And at time t is equal to 0, you also require that integral minus infinity to infinity dz times c has to be equal to m. Okay. That mass concentration condition has to apply even at t equal to 0, because that is the mass that has been injected. Okay. Now, these two put together, okay, you can represent the concentration as C is equal to m times delta of z. Okay. Okay. Where delta of z, okay, is what is called a delta function. Okay. It's in order to not confuse with the other delta, I'll refer to it by its complete name. This is what is called a Dirac delta function. It's called the Dirac delta function. Okay. It is defined this way. Okay. Delta of z is equal to 0 for z not equal to 0, and integral minus infinity to infinity dz delta of z, this has to be equal to 1. That is the definition of the delta function. Okay. And you can see that when we write c as m times delta of z, you get basically this expression. Integral is m and c is equal to 0 for z not equal to 0. Okay. So the initial condition is what is called a delta function. That is, you have a finite amount of mass within an infinitesimal thickness. Okay. So that is what is called a delta function. So how do we solve this? Okay. As in the case of diffusion into an infinite medium, there is no length scale here. Okay. So therefore, I can define the scaled coordinate psi is equal to z by root of dt. Okay. There is a similarity solution for the that is a similarity variable for the z coordinate, z by root dt, because there is no length scale in the problem by which I can scale the z coordinate. Okay. So therefore, I have to define psi is equal to z by root dt. What about the concentration field? If you recall, when we did the previous problem of a constant temperature at z is equal to 0, we were able to scale the temperature by that constant temperature. In this case, we do not have a constant concentration at a fixed location. What we have is an integral condition. Okay. What we have is an integral condition, okay, on the concentration field. Okay. And therefore, that integral condition has to be used to scale the concentration. Okay. So, integral minus infinity to infinity dz into c is equal to m. Write z in terms of this variable psi. Okay, rewrite z in terms of this variable psi. I will get root of dt integral minus infinity to infinity okay, d psi times c is equal to m. Okay. Therefore, I can define the scaled concentration as c divided by m by root dt. Okay. This I can define as the scaled concentration. Okay. M by root dt is a mass per unit volume, because root dt has dimensions of length and m is mass per unit area. Okay. And if I define it that way, I will get the condition as minus infinity to infinity d psi c star is equal to 1. Okay. So, that is the integral condition, okay, and the boundary conditions are c star tends to 0 for psi going to plus or minus infinity. Okay. So, as you go further away, when z goes to plus or minus infinity, psi also goes to plus or minus infinity. At this location, you expect that c will be equal to 0. Okay. So, how do we solve this? Okay, the procedure is the same as in the case of an infinite medium. We have to define the derivatives of the concentration field in terms of C star and in terms of psi. Okay. Here it is implicitly assumed that C star similarity solution C star is only a function of the similarity variable psi. Okay. In the similarity solution, it is assumed that C star is only a function of the similarity variable psi. As you can see, the boundary conditions have been expressed all in terms of psi, okay, and now we have to express the equations in terms of psi. Okay. For that, we have to use differentiation by chain rule. Okay. So, partial C by partial Z is equal to partial of m by root dt times C star, okay, because C star is C by m by root dt. So, I can take the m by root dt out and I will get m by root dt, okay, because t and z are independent coordinates, partial C star by partial z. Okay. Partial C star by partial z, I can write that as partial psi by partial z d C star by d psi. Okay. And this in turn is equal to m by d psi by dz is going to be d psi by dz from this expression here. From this expression here, d psi by dz is going to be 1 by root dt. Okay. Therefore, this becomes m by dt d C star by d psi. Okay. For the second derivative, you have to do this once again. Okay. Partial square C by partial z square is equal to partial by partial z of m by dt d C star by d psi, okay, which is equal to m by dt d by d psi of d C star by d psi into partial psi by partial z. Okay. Is equal to m by dt power 3 halves, okay, d square C star by d psi square. Okay. Differentiation using chain rule. Okay. The third term is the partial derivative with respect to time. Okay. The third term is the partial derivative with respect to time. Okay. This is going to be equal to partial by partial t of m by root dt C star. Okay. And now note that within the integrand we also have a time dependent term over here. So, we have to take the derivative of that as well using differentiation by chain rule. Okay. Okay. So, the derivative of the first term 1 over square root of dt, t power minus half, derivative is minus half times t power minus 3 by 2. Okay. So, minus m by 2 root d t power 3 by 2 C star, okay, plus m by root dt. Okay. Partial C star by partial t is going to be equal to d C star by d psi partial psi by partial t. Okay. And simplifying this further, I will get minus m by 2 root d t power 3 by 2 C star, okay, plus m by root dt, okay, partial psi by partial t, substituting for psi from here. Okay. This gives me minus z by 2 root d, okay, t power 3 by 2, okay, into d C star by d psi. okay, and z by root dt is equal to psi. So, I will get minus m by root dt into psi by 2 dc star by d psi. Okay. This should be psi by 2 t, okay, psi by 2 t dc star by d psi. So, this is the second derivative with respect to z, this is the first derivative with respect to t. Okay. So, putting all that together, I will get on the left side, I will get m by root of dt, okay, into, there is a common factor of 1 over t on both sides. So, yeah, I have a root dt here and I have a 1 over t here. So, I can take that as a common factor. Okay. So, minus m by root d t power 3 halves, okay, into c star by 2 plus psi by 2 dc star by d psi. Okay. That is on the left hand side, that is the partial c with respect to partial t. Okay. I have simplified this partial c with respect to partial t over here. Okay. On the right side, I have the diffusion coefficient times d square t by dz square, that is this one. Okay. This is into m by dt power 3 by 2 d square c star by d psi square. Okay. You can see easily that m cancels out on both sides, and I have root d on both sides and t power 3 by 2. So, those all cancel out. Okay. And I will get my equation as minus c star by 2 minus psi by 2 dc star by d psi. Is equal to d square c star by d psi square. Okay. And this left side I can write it as, okay, as minus 1 by 2 d of c star psi by d psi. Okay. You can see that when you differentiate c star times psi, you will get c star plus psi times dc star by d psi. Okay. So, this is just a an integral of that. Okay. This I can integrate once because I have derivatives on both sides, and therefore, I can integrate this once to get dc star by d psi is equal to minus c star psi by 2, okay, plus a constant. Okay. That constant is fixed from the condition that, okay, the boundary condition, if you recall. Okay. C star goes to 0 for z going to plus or minus infinity, okay, or psi going to plus or minus infinity. Okay. When C star goes to 0, dc star by d psi also goes to 0, okay, and C star times psi also goes to 0, as we will show a little later. Okay. So, as z goes to plus or minus infinity, C star goes to 0 and the derivative also goes to 0. Okay. Therefore, this requires that C1 is equal to 0. Okay. So, this requires that C1 is equal to 0. Okay. And the equation becomes dc star by d psi is equal to minus c star psi by 2. Okay. dc star by d by, okay, integrating this is equal to minus psi d psi by 2. Okay. implies that log of C star is equal to some constant into minus psi square by 4 plus a constant. Okay. And if you exponentiate both sides, you get C star is equal to some constant C e power. Okay. Let me write this as, okay, not confuse. Okay. B e power minus psi square by 4. Okay. And now we have to determine what is this constant B. Okay. That has to be determined from the condition that we had. If you recall, in terms of the scaled variable, we had this condition that this one, that the integral of C star between minus infinity and plus infinity has to be equal to 1. Okay. Now, we know that this condition, integral d psi into C star is equal to B integral d psi. This is between minus infinity and infinity. Okay. D psi into e power minus psi square by 4. This has to be equal to 1. Okay. Now, this cannot be integrated analytically. However, the definite integral exists between minus infinity and infinity. The definite integral exists. Okay. And the definite integral is okay, integral minus infinity to infinity d psi e power minus psi square by 4 turns out to be equal to 2 root pi. Okay. 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 You cannot integrate the indefinite integral analytically, but however, the definite integral exists. Okay. And therefore, you get an expression for the concentration C star is equal to 1 by 2 root pi e power minus psi square by 4. Okay. And therefore, the concentration field C is equal to m by root dt into C star. Recall that we had scaled it by m by root dt. Okay. Okay. Is equal to 1 by root is equal to 1 by 2 root pi dt e power minus z square by 4 dt. Psi is z by root dt, therefore, psi square is z square by dt. Okay. So, this is the concentration field for this. Okay. So, this is the concentration field. Solution for the concentration field determined using a similarity solution. Okay. So, if I plot, so I'll just plot it as a function of z. I'll put z on the horizontal axis here. Okay. I'll put z on the horizontal axis and the concentration on the vertical axis. At initial time, you have the concentration all concentrated at this particular location. It's a delta function. As time progresses, the concentration spreads. Okay. The concentration spreads with time. Okay. So, as time progresses, the concentration goes in this direction with time. Okay. So, it spreads further and further. The extent of spreading, okay, the extent of spreading, okay, I'm sorry, I should put the m here. Okay, there is an m. Okay. Now, to find out the extent of spreading, we can calculate the standard deviation or the variance of this spreading. Okay. This function, okay, this function, it is called a Gaussian function. Okay. This function is called a Gaussian function. Okay. It is a bell shaped curve with a maximum at the center and which decreases to 0 on both sides. Okay, Gaussian function. In order to find out what is the extent of this spreading, we can calculate the standard deviation. Okay. The standard deviation in the z direction is equal to integral minus infinity to infinity dz z square times c divided by integral minus infinity to infinity dz c. Okay. That is the area under the curve. Okay. You can write this either in terms of z or in terms of psi. Okay. It does not matter. Okay. Once again, this is an indefinite this is a definite integral which can be solved. It has to have dimensions of z square. Okay. It has to have dimensions of length square, and it has to depend upon only the diffusion coefficient and time. Okay. So, just by dimensional analysis, this has to be d times t, because once you have integrated, the resulting expression cannot depend on z, because you have already integrated over z. So, it can depend only upon the diffusion coefficient and time, and there is a constant in front. That constant turns out to be 2. Okay. This is the standard deviation. This is the variation in the z direction, the variance. Okay. I will write this as the variance. Okay. Okay. Which means that the standard deviation sigma z is equal to root of 2 dt. Okay. So, basically the width of this Gaussian distribution increases as time increases, proportional to square root of 2 dt. The spatial extent increases as time increases, proportional to square root of 2 dt. Okay. So, this is the solution for the concentration field. Okay. So, this is the solution for the concentration field. Okay. For a configuration where the governing equation was partial c by partial t is equal to d partial square c by partial z square, and at t is equal to 0, c is equal to delta of z, okay, into m, okay, where m is the mass inserted per unit area, okay, where m is the mass inserted per unit area. Okay. Okay, so, this gives you the variation in the concentration field. So, basically if you inject a mass at a particular location, a plane, okay, mass per unit area injected at a particular location, okay, that will spread, okay, on a particular plane you are injecting a mass per unit area, and as time progresses the mass diffuses. The characteristic length scale for the diffusion once again is root of dt. Okay, the characteristic length for diffusion is once again root of dt. Okay. And as it diffuses, the mass remains a constant, total mass remains a constant. The concentration at the center, okay, at z is equal to 0 for example, the concentration, maximum concentration decreases 1 over root dt, extent of spreading increases proportional to root dt in such a way that the total mass is a constant. Okay. So, that is the solution for diffusion in one dimension. Okay. So, in the next lecture, I will discuss some aspects of diffusion in 2 and 3 dimensions. Okay. I will not go through the detailed derivations, but I will just tell you what the answers are before I go on to the next problem, which is diffusion into a finite medium. Okay. So, I will continue this in the next lecture. I will see you then.